Hello, um, welcome to the first lab for the deep learning course. Um, I'm Abhijit. I'll be the TA for this iteration of the course. Uh, so, um, so for those who are not familiar with this, we'll be using Google Colab throughout the course of the entire course. Google Colab is just a Jupyter notebook that's running on Google's c- compute backend instead of your local machine, and a Jupyter Notebook is just a interactive piece of software that you can use for running Python code. You can add text to it. You can do visualizations and all kinds of things. And so it's like really useful when it comes to data science and machine learning and that kind of applications. So for the first lab, the goal is to have a basic introduction to PyTorch. So PyTorch is the framework that we'll be using for the labs. So it's a deep learning framework that's made by Google. It's that's made by Facebook. It's open source and it's based on Python, as you probably know. Um, and so the goal for today is to get a basic introduction to PyTorch and maybe build a basic neural network that does classification. So we'll get started. So at any point, if my audio gets cut off, please do let me know because uh, my headphone port is not working correctly. Also, if I do make stupid mistakes, please point it out. That would be greatly appreciated. Okay, so first things first. So the most important thing that you have to remember is that before you start running any code, you should go to runtime and then you should change the runtime type to GPU. Uh, so for today's lab, it's not actually required, but then in future labs, when you're dealing with uh, bigger models that will require more and more computational backend, so then you'll have to use a GPU. In which case, and if you try to run it on a CPU, it will be extremely slow. So keep that in mind. So if you click connect, it will connect to a machine. Um, okay, it's fine for today. I guess we can use without a GPU. Okay, so to use Torch, you have to first import it. So you go import Torch. And Torch is already pre-installed on all Collab instances, so you do not have to explicitly go and install it. So the basic units in PyTorch are what are called tensors. So we'll first look at tensors. So what is a tensor? A tensor is basically like a multidimensional array. So you can have a big array, so n dimensional array. So how many dimensions it has is up to you, and it contains numerical data, and you can do various kinds of operations on this numerical data. So it's kind of like NumPy arrays, but then with more functionality built into it. So let's make sample tensor. So for example, uh, so we can have a tensor of any shape. So say we make a tensor of shape 7, 9. So this will be a 7 by 9 tensor. It will be a 2D tensor, and you can print out your tensor and see what it's made. So you can see that it has made a 7 by 9 dimensional tensor, and it has populated. So the values that are currently showing, these are these are not random values. So when you're creating a torch tensor and and it is uninitialized, then the content that is present in the tensor will be whatever that was originally present at that memory location. So you should always remember that an uninitialized tensor and a random tensor are different things. So just by creating a tensor does not mean that the contents of the tensor are random. So if you want to create a random tensor, then you have to explicitly make a random tensor. So if you want to create a random tensor, you go torch.rand Then you specify the shape whatever you want. So say we are creating a 7,9 tensor. Now if we look at what the tensor has, you'll see that there are, so what it does is it populates it with random numbers between 0 and 1. So if you want to look at the shape of a tensor, you can look at the shape attribute. You can also use something called size. So in fact, these two are equivalent, so you can use either of them. In shape is just alias for size, and this was actually added later on so that it's analogous to what is present in NumPy. So in NumPy, you do dot shape to look at the shape of NumPy arrays, and similarly, you can use dot shape to look at the shape of torch tensors. So that's on how to create a basic tensor. So now we can look at so how to do certain kind of operations on tensors. Um, so any operation that you do on a tensor, you can do it in place, meaning you can do it with. So wait, I'll give you an example. So we created a tensor called my tensor. So let's use that tensor. Let's call the random function on it. So what happens here is you're calling an in place function on my tensor, and you're passing in 10 as an argument. And so what happens is now what my tensor contains is this. So you're populating my tensor with random numbers up to 10, up to but not including 10, and the value is implicitly assigned to my tensor. So you do not have to explicitly assign the output of this function to a new variable. So that is why it's called an in-place function, because it mutates the tensor in place instead of. So any kind of in-place functions, it will in PyTorch they will be post fixed with a underscore. So this is how you fill it with random numbers. So there are other kinds of in-place functions that you'll commonly use. So if you want to fill a tensor with zeros, so you can just go my tensor dot zero underscore, and it will fill the entire tensor with zero. Yes, the meeting is being recorded. It is being recorded. Okay. Yeah. So yeah, so you can use this to fill a function with zeros, and similarly, if you want to fill a function with ones, you can do that as well. You can use a function called fill underscore again, and you can fill it with any number. So if you put 1 in here, it will get filled with 1. A very important thing to note is that if you want to create a copy of a tensor, you cannot just do my tensor 2 is equal to my tensor, because this will point to the original tensor itself. So if any changes that you make to my tensor 2 will create changes in my tensor, because it's pointing to the same thing. So if you want to create a copy of a tensor, then you have to explicitly call the copy function. uh, I'm sorry, it's not copy, it's called clone. Yeah, right. So now my tensor 2 will be a copy of my tensor. Yeah. um okay, so now we can look at basic constructors. If you want to create various types of tensors, then there are many inbuilt constructors that are available in PyTorch that you can make use of. So you do not have to explicitly come up with logic to make tensors. There are many constructors that are inbuilt to PyTorch. So we can look at a few commonly used constructors.
Sir, if possible, can you zoom your screen a bit?
Yeah, sure. That's fine.
A bit more, sir.
Please don't call me sir. I'm just in fourth year, so yeah. Uh, so right. So I'm hoping it's visible now. So there are many constructors that are already inbuilt, so we can look at a few of them. So for instance, if you do torch dot range, and you can have, so what happens is it basically gives you a range of items. So it starts with 3 and it goes up to 10, not including 10. If you, so you can see that these are integer data. So if you want it to be float, you can just add a, just do 3 dot, and it will automatically make all the elements of type float. So you can see here that you made a tensor using a constructor, and similar to this, there are like many kinds of constructors. So if you want to get a equally distributed tensor between two values, you can, there's something called a torch.linspace. So what that does is, say you want to start at 3, you want to go till 8, and you want 20 values starting from 3 to 8 that are equally distributed between them. You can use this and it will give you, so it starts at 3, it goes till 8, and there are, yeah.
So, what's the difference between a NumPy array and a tensor?
Um, so so the whole point of using PyTorch is for doing deep learning. And so when you're using NumPy arrays, a thing that's lacking is tracking of gradients. So when you're using PyTorch tensors, tensor is not just what you see, the data that you see here. There's a lot going on in the backend. So you can, so every tensor has a corresponding gradient function, and it'll also have corresponding gradient that is uh, associated with each tensor. And when you're doing operations on tensors, what happens in the backend is an acyclic graph is created that keeps track of how each tensor is being made. And so when you want to do model training, when you want to do back propagation, so, and when you want to calculate gradients, PyTorch has a functionality in which it can automatically do that for you, and it needs to use these gradients that is there to do back propagation. So if you're using NumPy arrays, you'll have to explicitly implement backpropagation. And if you're using Torch tensors, Torch has functionality to do it implicitly for you. And that's like one of the reasons. There are many reasons, but then this is the main reason that you'll probably use.
Makes sense.
Okay. So another thing that you can do is, so the shape of this array is 20, which means it's a one-dimensional array of size 20, and not an array, a tensor of size 20. You can use the dot view function to change the shape of an array. So in this case, you can make it 5 comma -1. So what happened here is, you're telling PyTorch, you're telling when you're telling the function, make the first dimension of this tensor 5, and when you, and you're following it to the -1. So what the -1 means is that make the second dimension whatever you want, such that the data is conserved. So originally you had a 20-dimensional data. So if you're making a 5, if your first dimension is 5, then automatically the second dimension should be 4, because you have 20 elements. But you do not have to explicitly calculate this. You can tell PyTorch the first dimension should be 5, and the second dimension, calculate it for yourself, whatever it has to be. So it does not have to be a two-dimensional tensor. You can reshape a 2D tensor to a 3D or a 4D tensor. So say you want to make it a 5 comma 2 comma 2 tensor. So you can say 5 comma 2 comma -1. And so here also PyTorch will automatically calculate the last dimension for you. So if you look at the shape of the tensor, you'll see it's 5 comma 2 comma 2. Okay. There are many other constructors. So if you look at torch.I, so what that does is it creates a diagonal matrix of size 3. This is just basically a 3 by 3 tensor, and the diagonal elements are 1. And there are a lot of constructors that are available, and you should check them out. Oh, so before I forget, you have, so what you'll be referring to for your quiz, as well as for the rest of whenever you use PyTorch, you should also always refer to the documentation because it's extremely well written, and there's a lot of things that you'll miss, and there's a lot of functions that you can make use of that might not seem obvious, but then they speed up your computation a lot. So just use the documentation whenever possible, and you can find a lot of these kind of niche functions that you can use in the documentation. Okay, cool. Now let's look at how we yeah,
I just wanted to ask, in the length space function,
right.
is the starting and ending value always included, like 3.00 and 8.00?
I'm not sure I understood. So you're asking whether 3 and 8 will always be included.
If you remove the view part, then
Okay,
the values it gave us 3.00, then there were 18 other values, and then 8.00.
right.
Yes.
Yes.
So the starting and ending values are always included.
Yes, that's how it works. Because you're splitting, so you're taking the start as 3 and taking the end as 8, and you're basically generating 18 values in between them. So if you want to generate 20 values in between them, then you put 22 here. That makes sense.
And the view part,
Right.
like view just changes the dimensions.
It changes the shape of the tensor. Yes.
So if for the 5 comma minus 1, the first dimension was 5, and the next dimension the program can figure out the next.
Yeah. So if you put it as -1, you have to put -1 there, which tells PyTorch that you have to figure it out yourself.
So what happens when we do 5, 2, and -1?
So 5, 2, and -1. So now you tell the first dimension should be 5, the second dimension should be 2, and the third dimension you should figure it out. So there's no constraint that you can only shape a two-dimensional tensor to another two-dimensional tensor. You can reshape it such that you can reshape a one-dimensional tensor to a 4D tensor, 5D tensor, whatever you want, because it's just data and memory, right? So how you look at it, so you can shape it. So the shape of the tensor you can specify how you want.
So this converts this tensor to a 2 matrices of 5 cross 2.
Uh,
Two
kind
matrices
of
5.
like that, yes. So if you want to think about it like that, yes, you can. So but then if you add another 2, or so now you'll have a 4D tensor. So you can keep adding dimensions like this is what I mean to say.
I gives an identity matrix
Right, yeah. I mean, so if you want to look at something, just go torch.i in the documentation, and you'll see there'll be like extensive documentation on what it does. So you can see it returns a 2D tensor with ones on the diagonal and zeros everywhere else, and you can see what all inputs that it takes. So it takes n, which is just the number of rows. There are other optional arguments as well, which you can use, and you can also see what are the default values of these optional arguments. And there'll also be examples, so you can always look at the documentation to figure out. If you don't know what a function is, you can always look at the doc.
And then in this case, if I just said view 5, so
Uh,
that won't be enough. Would it give an error? View 5.
because you're starting with size 22 or in early case 20, and you're trying to reshape it to 5, which is not possible, right? Because you have 20 elements to start with, so 5 does not make sense. It does not automatically, so you have to specify -1 here. Otherwise, you can explicitly say, oh, convert it to 5, 4, then it will do that. That's fine. Cool. Okay. So, right. So now we can look at how we can move torch tensors to GPU. So you won't be always doing operations on the CPU, because then it would be extremely slow. So the whole point of using PyTorch is that maybe you can use GPU for your computations. So firstly, how do you check if your GPU is available in the background? So you can do torch. I'm sorry. So moving to GPU. So how do you check if your GPU is available? So you can go torch.cuda.is available, and this function will tell you if the GPU is working in the background and is correctly configured. So in this case, because for some reason Collab is not letting me use the GPU runtime, it says false, but then it should say true here when you try to do it. And so you can specify the device like this. So you can say torch.device. So if if torch.CUDA is available, which will be true if CUDA is available, then you CPU. So what this does is, so if CUDA is available, which means, so if there is a GPU that's available, and we are assuming that there's only a single GPU available, so you assign the device as CUDA 0, which means 0th GPU. And if it's not available, so like in our case, because for some reason there's no GPU, so you get CPU. And so if you look at device, say that you can see it's soft type CPU. And the reason we need to do this is because you by default tensors are not loaded onto the GPU, and you will have to explicitly load tensors onto the GPU so that the calculations that are done on these tensors are performed on the GPU. So the way you do that is you do so we all have already made a tensor called my tensor, so you can say my tensor dot to device. So what this to does is it loads whatever tensor you're using onto the device that you're specifying. So in our case, we do not have a GPU available, so but then if there was a GPU available, then it gets loaded onto the GPU. Another way to do this would have been to do mytensor.CUDA. So I can't run this because there's no GPUs available in our case, but then if you do this, usually this should also work, assuming you have a single GPU. Dealing with multiple GPUs, we'll do that in a later lab. So right now, any kind of models that we'll be training will make use of at most, will more easily fit in the GPU that's provided by Collab. So right now we'll stick to a single GPU. There are tensor operations that you can do. Okay, so new section. So let's make two tensors, torch.rand. Let's make a 4x5x2 tensor. Let's make another tensor B, which is also 4x5x2 tensor. And you can do almost all of the operations, arithmetic operations that you can think of. So addition, add to tensors. There are multiple ways to do arithmetic operations. So you can use the plus operator, or there are specific functions in PyTorch that you can make use of. For example, if you do torch.add a comma b, then that does the exact same thing. There are also in-place operations that you can use. So you can do a dot add underscore b. So this will add b to a, and then it will store the result in a implicitly. So you can see the results of all the three operations are the same. And so you can do all kinds of things. You can do element-wise multiplication, you can do matrix multiplication. So for example, if you do, let's take two tensors, T1 is torch.rand. It's a 4,5 tensor, and you take T2, which is another tensor, which is say 5,7. So these are compatible for multiplication because their dimensions are same. So you can see 4,5 times 5,7 tensor should give you a 4x7 tensor. So you can do multiplication using the add symbol. So you can do T1 add T2. It will give you another tensor, and say this is T3, and you can look at the shape of T3, and you'll get 4,7, which it should be after matrix multiplication. Element-wise multiplication is using the asterisk symbol. So what would you normally use for multiplication? That performs element-wise multiplication. So you can do element-wise multiplication between A and B because A and B are of the same shape. So you can do element-wise multiplication. So you can say A times b, and say this is c. So you'll get another tensor of the same shape because you're performing element-wise multiplications on each individual element of a and b. So this is to do with the basics of tensors. Like there's a lot more functionality that you can look at in the documentation, and you'll probably have to for the quiz. Um, okay, so now we can look at the most important part of PyTorch, which is autograd. So what is autograd? So autograd, by the name itself, you must understand what it does. So it automatically computes gradients for you, and by grade. So in when you're doing optimization problems, and specifically optimization for deep learning, most or all of the optimization algorithms that you use, like gradient descent or adam or whatever kind of optimization algorithm you use, you'll be making use of gradients. And one thing that you can do is you can implement functions yourself that compute these gradients, or you can use a deep learning framework like pytorch that automatically computes these gradients for you, which is much easier. So we can look at a simple example of how autograd works. So let's make a tensor. Say a simple tensor torch dot once. So what the once does is it makes a tensor where all the elements are one. We can make a 3 by 3 tensor, and we can specify that this tensor requires gradients. So when you're creating a tensor, you can specify in the constructor that this tensor requires a gradient, which means that when you're doing computations on this tensor, please keep track of gradients for me. You're telling PyTorch to do it explicitly. So now let's say we create a new tensor y by adding 2 to all the elements of x. Right. So now you've created y from x, which means that you can differentiate y with respect to x. And so if you were to do this manually, you can do that, or you can make use of PyTorch autograd functionality. So if you look at y's grad function, you'll get add backward. So basically, y was created by an addition operation, and PyTorch keeps track of this. So let's say we make another tensor z. Again, you're creating a new tensor using y. So you create a new tensor, say from y times anything 1.5, and then you say you create fourth tensor out. So you do z dot mean. So what mean does is mean takes all the elements and takes the mean of all the elements of a tensor. So if you have a tensor of say 3 by 3 shape, it will take all the 9 elements, it will add them up, and it will divide by 9 to give you the mean. All of these are differentiable functions, obviously. And PyTorch is keeping track of all the operations that you're doing. And so if you look at the grad function for out, so let's say it's mean, which means PyTorch knows how to differentiate the mean function. Um, so now that you've done all these operations, you want to calculate gradients or derivatives. So how do you do that? So what you do is you say out dot backward. So the backward function, what it does is it calculates the gradients for all with respect to all the variables that has been used to compute this set tensor. So to compute out, we have used z, we have used y, and we have used x. So it will compute the derivative of out with respect to all of these uh, variables or tensors. Okay, so that's it. So you've computed all the gradients. So now how do you look at the values of these gradients? You can do that so say you want to see the gradient of with respect to x. So you can say x dot grad. So this is the gradient of out with respect to x. And similarly, you can look at any function. Yes. Okay.
Sir, that part can you repeat the backward part and like
Right.
the gradient function
Mhm.
after
So
the mean?
okay. So you've done a series of operations on different tensors, and you've gotten this tensor called out. That part is clear. Like you've done various kinds of operations, and when you're doing various kinds of operations, you can always differentiate them. I mean, these are all different. What all operations we have done? These are all differentiable operations. You've added, you've multiplied, you've taken a mean. All of these are differentiable operations. And so when you want to calculate the derivative, you either you can do it explicitly. So you can say, oh, look at, so you've taken you have done you have done an addition, and you know how derivatives work with respect to addition, and so you can do that manually, or you can let PyTorch figure it out for you. Oh, so you can say, now that I've computed this new tensor called out, please calculate the gradients with respect to all the variables that I've used till now. So I want to calculate the gradient with respect to x. I want to calculate the gradient with respect to y. I want to calculate the gradient with respect to z. I want to calculate the gradient with respect to all the tensors that I've used to create this out. Does that make sense? It's basically
Yes, sir.
partial derivatives.
Yes, sir.
Okay, so PyTorch does that automatically for you, and so you do that. So you calculate gradients by explicitly calling this function called backward. You call backward on your final result, and so what happens is, so I told you PyTorch is keeping track of all the operations that you're doing at each step to create every tensor. So it will automatically traverses a cyclic graph of computations that you've done, and it'll calculate the gradients at each step. And you can look at what gradient it has calculated by using the dot grad. So every tensor has this attribute called grad, and when you do, after you do dot backward, you can look at this grad to see what is the explicit value of this gradient. I hope that's clear.
Yes, sir.
So there's this library called Torchwiz, and using that library, you can just look at the graph of combinations of like basic operations. So the way to install it is you can use pip, which is a package manager for Python. So you can say pip install Torchwiz. Uh, so the reason I've put an exclamation mark here is because this is not a pip install is not a Python command. You're running it in the uh, on the machine in the background. So basically, how you do, like, so if you have a Linux terminal, how you go like ls and so on, you basically do that. So if you want to run an ls here, you have to first have an exclamation mark, and then you go ls, and so it will tell you you can do any kind of Linux commands that you usually do, like print working directory or whatever. Okay, so we've installed this library called Torchwiz, and what we want to do is we just want to make use of a function from Torchwiz called make dot. And so we just want to visualize the computations that's happening in the background. So you start with x, and then you do y is equal to x plus 2, right? So you can see, so you start with x, which is a 3 by 3 matrix, 3 by 3 tensor, and you're keeping, so PyTorch keeps track of all the operations. So you can see here, it's basically made a graph of operations that you've done to get the y. So you have done an addition operation, which is why it says add backward. So you can run this on out as well. So it says you've taken started with x, you did an addition, and then you did a multiplication, and there are two arrows because you did y times y, so it's being used twice. And then you did another multiplication with 2, and then you computed a mean, and you got your result of out. So it's just a basic function that you can use to visualize like small computational graphs like this. Right. So I'm not recommending that you use this. I just use this so that just to get a basic idea of what's happening. So another thing that you can do, or say we have two torch tensors, torch dot ones, 2, 3, and you have say another tensor of torch dot ones, 3, 2. So you can see these are multiplication compatible. So because it's 2, 3 and 3, 2, you can multiply them to get a tensor which is of shape 2, 2. Okay, so if you do not want gradients to be computed, what you can do is you can say with torch dot no grad. So this is a context manager. So you can use this. So what this tells us, do not compute gradients for any of the operations that I'm going to be doing on these tensors. So if I say t is equal to a multiplied by b, a multiplied by b, and if I do t dot backward, so I'm telling PyTorch go and calculate the gradients with respect to a and b. But then it won't work because you have explicitly told PyTorch when you were doing this operation to not calculate gradients. Yeah, right. So this is how you do that. So in many, so in cases where you're doing, so example, if you're doing inference on a model, and then you do not want to calculate gradients because it's a lot of unnecessary computation. And so in such cases, you can tell PyTorch explicitly not to calculate gradients using torch.nograd, which is self-explanatory from the name, I guess, because it's saying nograd. Okay. So this is basics of AutoGrad, and I think we've covered like basics of tensors, basics of how to do computations on tensors, how to calculate gradients, or we almost never have to explicitly calculate gradients. It's always done in the background for us. So this is just to see what's happening. So now what we can do is we can try to apply a neural network to a simple problem of MNIST classification. So many of you must have heard about MNIST classification. It's a very basic data set of there are, I think, 70,000 handwritten images. So there are 70,000 images, and each image is a handwritten digit from 0 to 9. So you have images of handwritten digits, and your goal is take an image, pass it through the model, and the model should predict what number is there in the image. So if there's a 3 written in the image, then your model should say, oh, there's a 3 written in the image. Okay. So we can look at the okay. So let's look at the MNIST dataset. So MNIST dataset is a pretty standard dataset. It's a very small dataset, and so it's already inbuilt to Torch Vision. And there are so many such standard datasets are already inbuilt, and you can access them using Torch Vision. So you can go. Okay, let's just do this for now. Right. And then you can create a. So I'm not sure how much Sir has covered in the lectures, but when you're doing training, when you're training neural networks, you usually have a training set, and you'll also have a test set. And training set is the data that you'll use during training. This is the data that you'll be using to train your model, basically. And test set, your model never sees the test set during training. The test set is only used to evaluate the performance of your model. So I'm not sure what Sarah has covered in the lectures, but then this is just a basic thing that you should probably know. So like I was saying, MNIST is already present in Torch Vision, so you can directly use the MNIST dataset. So how you use it is you can go train set is so you have to create separate train and test sets. Train set is list of you can specify some path. Say train is true. You can also have a test set. Yeah, right, true. So all this is doing is it's just downloading the data set, downloading the corresponding train and test sets of this data set. So if you want to see how the data looks like, yep.
In this case, aren't both the data sets the same because we specified the same path? Or...
No, you're just telling it where to download it to.
Oh, okay. So what determines which of the examples go in train set?
It's already predetermined because so a data set in PyTorch means that we have already explicitly told we've explicitly encoded what samples you need in the training dataset and what you need as test dataset. So in this case, so MNIST is a data set and which has a train and a test split that's already, so it's standard what the train and the test split is. So like you do not have to explicitly do this, but when you, in the future labs, when you're working with like very niche kind of data, then you will have to explicitly specify, oh, take these many images, make it the test set, take these many images, make it the train set. And you can also specify what images you want to be in the test set or what images you want to be in the train set. But in this case, because it's a very, very standard data set, it's already predetermined. Uh, that's why it's being done like this.
Okay.
Yeah, cool. So you have a train set and a test set, and if you want to look at what your data looks like, so you can say train set. So let's look at an image from the train set. So your train set has, so there are two. So your train set has data, which is the, yes.
So if all of it is predetermined, will everyone get the same result when we all run it? Because the training set and testing set is already decided.
You will get the same result if when you're running it, depending on certain factors. So there will be slight variations because your model might have many stochastic components. Like for example, if you're having dropout, so there are many components that have certain random functionality to it. So which means that the random functionality will be different for you and it will be different for second person who trains the model. So if your model does not have any such random functionality, plus so there's another thing, when you're initializing your model, the weights that you're assigning to your neural network will be random in most cases. And so because you're starting with different random weights, then you cannot assure that everybody will get the exact same result, but it will be almost in the same ballpark.
Okay, thank you.
Right. So your train set has dot data. So that's data which corresponds to the images. And let's take a look at a single image. And so this will be a tensor, obviously. And this tensor corresponds to an image. And you can visualize this image. And for visualizing this image, first you'll have to convert it into a image object. So how you do that is, okay, so again, torch vision has a function that's already implemented for this. So you can use transforms, and I think it's called 2PIL image. So what this does is takes a tensor and it converts it into a PIL image. So you want to run this on this thing, it's tensor. Let's see what happens. Right. So I don't know if you can see this, but right. So this is a sample from the training set. So you can see this is a 5, and similar to this, there will be images corresponding to different digits. So you do not have to know what exactly this is. I just use this so that you can look at the data. So it's not important right now. Yes, Srishti.
What does 2PIL mean? Like, what is PIL?
So it's like, so currently your data is in the form of numbers. It's in the form of tensors, and you cannot directly. So you want to convert this numerical data into an actual image. That's an image. Like say you have a JPG image or you have any kind of image. So if you want to visualize this image, you cannot directly do that from a tensor. You have to first convert it into any kind of image. So to do that, so there's a library called Pillow, which is used in Python, which is used for various kinds of image manipulation tasks. You can open images, you can do various kinds of stuff with images. And so in Pillow, so basically what I did here is I used a transform which converts a tensor into a pillow image. And when you convert it into a pillow image, and then you can visually look at the image, because you cannot visually look at a tensor, right? So it's not important. Just understand that I just converted a tensor to an image. It's not important right now because we're not dealing with computation in specific. We're just dealing with I just wanted to look at what the data is. So it's not important. We'll look at torsion transforms in a later lab when we need to do computation specific stuff. Okay, so let's just ignore that. So I just wanted to look at what the image is. So similar to this, you have 70,000 images of digits, and so now you want to split this into a training set, a validation set, and a test set. So a training set, a validation set, and a test set. You usually do this when you're training deep learning models. It's a standard practice to train your model on a training set and then fine tune the model on a validation set and then check your performance on a test set. So fine tuning, I'm not sure how I'll explain it right now to those of you who are not familiar with it. So let's just say uh, that we're going to report our performance on the validation set. So at each step of training, you're training your model, you're using the training data to train your model, and you want to see how well your model is performing on new data that the model has not seen. So we'll use validation data for that. Okay. So you downloaded your data set. You have a train set and a test set, and we'll create. Yes.
Sorry to disturb. How long is the lab?
It's supposed to be 2 hours. Yeah.
And the quiz will be after that.
It depends on when the lab finishes. So if it finishes before 2 hours, then we'll have it within those 2 hours. Otherwise, like the quiz is pretty short. It's only like 15 minutes, I think. Okay. Okay. So you have downloaded a dataset, and let's create like so the dataset is pretty big. Even it's like 70,000 images, and for the purposes of demonstration, we'll choose a very small subset of this dataset because we do not want to waste time spent training on the entire dataset. And because we're doing a live demonstration, let's take a very small fraction of this dataset for demonstration. So what I'll do is I'll take the train set and I'll take just the first 1,000 images. Okay. And I'll make a training set out of this. So I'll take the train set, I'll take the first 1,000 images. So dot data means that you're accessing the images, not the labels. You're accessing the images. And you take the first 1,000 images. And so earlier we were looking at a single image, right? And so what is the shape of this tensor? The shape of this tensor is 28 by 28. So every image is of shape 28 by 28. So it's 28 by 28 pixels. But then when you're passing it to a neural network, you do not want it to be a image. So you do not want it to be a 2D tensor. You will flatten it out. So instead of it being 28 by 28, what you'll do is you'll make it 1 by 784. So 28 times 28 is 784. So you'll have the same data, but then instead of being in a 28 by 28 format, you'll make it 1 by 784. Yeah. So how you do that? You know how to do that. You use the view function. So you say view minus 1 comma 784. So you say I want the last dimension to be 784. What are the remaining dimensions? You can figure it out, and you'll also make it a float. And then the corresponding labels. So your images will have corresponding labels. So which means that if you take an image and the image contains a 3, then there should be a label which says that, oh, this image contains a 3. So you need those labels as well for training. So you have labels, and again the first 1,000 labels. Yeah, I think it's called targets. Yeah, right. So if you look at what is there in train Y, it says 5. So we visualize the first image, and it was a 5. You saw that it was a 5, and so you need to tell your model, okay, this image contains a 5, and so you have a label for that, and that is what is there in train Y now. And similarly, you can make a validation set. So similarly, you can take a validation that's and instead of first 1,000, let's say the next 500 images you'll take, and again you'll reshape it so that its size is 784, and you'll again have labels for these validation set. Right. I've created a validation set as well. Okay. So now what we can do is we can set it out. Yes.
So where are we reshaping to 784?
Because you're passing it to a neural network, and so right now the kind of neural network that we're going to use is called a fully connected network. So when you think of a neural network, so if you just Google neural network, this thing that you see, this is called a fully connected network. There are other kinds of neural networks which we'll deal with later, but right now we'll be using a simple kind of neural network, the simplest kind of neural network, which is called a fully connected network. And it's also called a multi-layer perceptron. I don't know what Sar is covered in class. So when you're passing inputs to this neural network, you have to pass a single vector. You have to pass a single dimensional vector. So if you're passing a single dimensional vector, you cannot pass a 28 by 28 tensor to it. You have to pass it in a single. So it has to be a linear tensor. Do you understand what I'm saying? Like it has to be. So it has to be something like. It has to be like a NumPy array, a single dimensional NumPy array. But in this case, a single dimensional torch array, torch tensor. So you're passing a single dimensional torch tensor to this neural network, and it'll do various kinds of operations on it, and you'll finally get some output.
So the images are 28 by 28 pixels.
The images are 28 by 28 pixels, yes. And you're not passing 28 by 28 to it. You're resizing it. You're reshaping the tensor so that it's a 784 size tensor instead of a 28 by 28 two-dimensional tensor.
So and the float, that's just a syntax.
What is syntax? Float. Oh, okay. So I did dot float so that it's converted. So all the numerical data within it is of type float.
What is passed in neural network is float only.
I mean, it's not specifically like that, but just for convenience.
The training set y that stores the labels.
Train Y.
Train y.
Yeah. So we have in trainets we have the image data, and in train Y we have the corresponding labels of the first 1,000 images.
So the targets is a part of the tensor only. Because train y is just the label.
No. So these are not tensors. So train set is it's not a tensor. So if you look at type of train set, so it's a datasets object. It's not a tensor. The tensor is contained within it. So if you do train set dot data, what you get? Wait, let me show you. So if you do type of train set dot data, now you get a tensor. So train set itself is not a tensor, it's a object and contains an attribute called data, which is a tensor.
So train set contains something else also.
Which contains something else?
Train set is an object which has a tensor called data.
Which has an attribute called data, which is a tensor.
Okay, so does train set have something else also?
Yeah, train set has something else. So that is how we how we got the targets as well, right? So you have train set dot. So train set is actually an object. That's various kinds of stuff. So if you look at train set dot classes, so it will tell you what classes are there in the data set. So you have classes meaning, so what labels, what different kinds of labels are there. So you have digits from 0 to 9. So you have corresponding classes. And similarly, you also looked at targets. So this tells you what are the labels corresponding to each image that is there in the train set data. What are the labels corresponding to each of those images you'll get in train set targets. It's just an object, so you do not have to worry about it. You're just using some dataset object. so it'll be different in each case, right? So when you're implementing datasets by yourself, you'll make it such that you, in some way, you can get this data in the form of tensors. So you do not have to bother with all of this other stuff. What you have to understand is we have finally got our data such that each image is a tensor and the corresponding label is also a tensor. Right. So we have created two separate splits of the data. One is a train split and one is a validation split. So train split contains a set of images, 1000 images, and our validation split contains a set of 500 images. Okay. Right. So we've made two splits. So now what we can do is now we need a model to train. So we need a neural network model that will be passing all this data to train. So we'll make a neural network model now. Okay, so for making our model, we'll need to import some stuff from PyTorch. So we'll do. So we already imported Torch. So we'll need a module called NN. We'll also need another thing. So we're just importing a few modules that we'll be using. Okay, so now let's implement the actual model that you'll be training. So there's some neural network model to which you will be passing images and which will tell you what the image contains. And to train this image, you have already loaded all the data that you need. So now you need to pass this to some model to train it. So let's make such a model. So models are implemented as classes. It's usually convenient to implement models as classes. So let's implement a class called classifier. And what this class does is it implements a model. It implements a neural network model that will take in 784 size images and it will give out labels from 0 to 9 telling you which digit is there in the image. That is our goal. So for our this classifier class inherits from an n.module. So every time you're making any kind of neural network module, in any kind of neural network, you'll have to inherit from this class called nn.module. Yes.
So this class that we'll be making, this will represent the entire neural network.
It will
or only
represent
one
all the
layer?
functionalities associated with that model.
Okay, so the entire model will be.
The entire model will be implemented inside this class. Yes.
Okay.
And so we'll have an init method. So I'm assuming you guys know this because there was a lab 0. So you must know what an init method is. And so what all are we passing to this model? So when we're creating a model, the model has to know what kind of data it's going to be receiving and what the output should be. So this model should, so when you're making an object of type classifier, you have to tell it what kind of input it will be receiving. So in our case, it's a tensor of size 784. But then we do not want our classifier to be we do not want to hard code that 784 here. So we'll just put number of features. So here, when you're making a model, we'll pass in 784, but then it can be anything. We can pass in different size tensors as well. And you'll have hidden layers. So let's say we just have a single layer with a number of hidden units. And you'll also have output. So this corresponds to the number of classes. So in our case, it will be 10 because we are predicting from 0 to 9. Okay. And let's call the constructor for the superclass. Okay. Now that we've done this, we can create, so we can make our neural network here. So how we do that is we can say self.net. So you do nn.sequential. So the reason you use sequential is because you can put multiple layers inside sequential. So in a neural network, so let me just go again to neural network. Right. So a neural network will have multiple layers. So there'll be layer 1, there'll be layer 2, there'll be layer 3, and you want to pass your input through these layers sequentially. And so basically, you want to apply layer 1 first, you want to apply layer 2 second, you want to apply layer 3 third, And so you want to apply these layers sequentially. So when you put it inside NN.sequential, any layers that you put inside NN.sequential will be applied sequentially to your input. So first you pass it through a so this is called, so in PyTorch, this fully connected network is called NN.linear. So it's implemented as NN.linear. Right. So you're passing in your input is of some size, which you have passed in as number of features, and you want so let's assume our neural network has just one hidden layer. So let's assume our network is like this, and there's just one hidden layer, and let's say this hidden layer has some hidden number of units. So these are called units or nodes. So there are, like, say, hidden number of nodes in your hidden layer. So first what happens is you take an input which has size, number of features, and then you want to convert it to hidden number of units. I think I have misspelled this here. You go hidden, and then you want to apply another linear layer, another fully connected network here, another component of fully connected network here, which converts this from hidden number of units to your final. So how many outputs do you want? You want your outputs to be of size 10, because you're predicting from 0 to 9. So you'll say num features, num hidden to the number of output, right? Basically what happens is you have defined a sequential network, and what the sequential network contains is it has two linear layers. And first linear layer, it takes in inputs which are of size, number of features, and it gives you a tensor which is of size num hidden. And the second layer, it takes in an input which is of size num hidden, and it returns the size output which is of size num output. And all of this you are specifying when you're creating the classifier. You will be specifying what is your num features, what is your num hidden, and what is your num output. All of this you will be specifying when you're creating your classifier object. Okay, so you've created a neural network. So one thing is missing here. So you've just created linear layers, but usually in neural networks there will also be something called a non-linearity, and I don't think sir has covered this. So I'll not explain what it is right now. So neural networks. So basically, neural networks can fit any kind of data. Theoretically, they can fit any kind of non-linear data, and to do so, if you only have linear layers, then you can only fit linear functions. In order for a neural network to be able to fit any kind of function in theory, then you need to have a non-linear activation function after each layer. And there are various kinds of activation functions. There's something called sigmoid, there's tanh, there's relu, there's elu, there's many kinds of activation functions. So here we'll just use something called a relu. So you do not have to bother what it does. It's just a function. It takes in some input and it returns an output, and it's a non-linear function. And sir will cover this at a later point of time, so you do not have to worry about it now. Just understand that it's just a non-linearity. It's just adding some non-linearity to your model. Okay, so every class that implements a neural network will also have to have a function called forward. What this does is it takes in an input and it calls your network on the function. So we defined a network, and it calls the network on whatever input you're passing. Okay. So now you can instantiate a classifier. So you can say our model is a classifier which takes in inputs of size 784. Let's say that the hidden layer has 512 units, and let's say the output should be of size 10. Okay, so now we've made our model as well, and let's try passing some random input to the model to see if it's working correctly. So let's create an input, just a random input, and let's say it's a random tensor of size 784 4. And the reason I've put 1 here I'll mention later. So it's a 1 by 784 tensor, and we're passing it through the model. Okay, and we'll get a tensor as the output. and the size of the shape of the tensor should be 10, and it's of size 10. And each of these outputs, so you get a tensor which is of size 10. So you have 1 number, 2 number, 3 number, 4 number. So you have 10 outputs, and each of these numbers correspond to each of the labels. So this corresponds to 0, this corresponds to 1, this corresponds to 2, and so on up to 9. Right. And our goal is, after we have trained our model, these numbers should tell us which digit is contained in the image. So you're passing an image to the model, and you get an output which is a 10-dimensional tensor with 10 numbers in it. And then this tensor should tell you, okay, this image contains a 3 or this image contains a 4. That is the goal after training. So you can see our model is working correctly. You have passed an input of size 784 through it, and you have gotten an output which is of size 10, which is exactly what we wanted. Okay, so the reason I've put 1 here is because usually PyTorch models expect a batched input. So what that means is you pass in not just one image, you pass in, say, 10 images at a time through the model, and you get 10 outputs at a time. So the whole reason for using GPUs is so that we can do faster and faster computations. So if you're passing images one at a time, it does not make sense, right? So you pass the first training image, you get an output. You pass the second training image, you get an output. That will be extremely slow. So what you usually do is, you, instead of passing one image at a time or one input at a time, you usually pass, say, a batch of images at a time through a model, and you'll get that number of outputs at a time. And so what then happens is it significantly increases speed of training. So you will have to train for much lower time if you're passing multiple images at a time through a model. So instead of having a 1,784, we could have had a 12,784 input. So which means that you are not just passing one image through the model, you're passing 12 images, each of size 784 through the model, and you can easily pass it through the model, and the model will give you some output which will be of then shape 12, 10. So there'll be 1, 10, there'll be a tensor corresponding to the first image, there'll be another output tensor corresponding to the second image, and so on. For every 12 images, every one of those 12 images, you will get a corresponding output of size 10. I hope that's yes.
What is the forward function doing?
The forward function is, so you have defined a network. You have defined a network here. You've defined what your network is, but then you want, so when you're calling your class model on some input, you need to take that input and pass it through the model, and you need to get the output, and you should return the output back. So that is exactly what the forward function does. So whenever you're implementing a neural network that's inheriting from an n-dot module, you have to implement a forward function that takes in an input and returns an output. Is that clear?
Yeah.
So for forward function, all the forward function does is it just takes your input, it passes through the model, and it does whatever it wants to the input. It passes through the model, and it gives you the output. It returns the output. That's exactly what we need. So when we're calling the model on any kind of input, implicitly the forward function will be called on input. And so once the forward function is called input, then you'll call this network on the input, and then you'll return the output. Somebody else raised their hand.
Yes. So in the forward function,
Yes.
how does it know to return a tensor of the number of outputs, or is it in the way that the NN library was implemented?
No, because here, so you know how so when we're creating the classifier, so you're creating a classifier here, and you're saying you're assigning 784, 512, and 10 to what? To number of features, number of hidden, and number of output. So when you're creating this classifier, this init function will be called.
Yes.
And so when this init function is called, so all this is contained within the init function, this much. So you're creating a network, and when you're creating a network, you're specifying here what the input size will be, what the number of hidden layers should be, what the output should be. All of this you're specifying when you're creating a network. and this network will be created as soon as you're instantiating this classifier, as soon as you're creating an object of type classifier with this input, then this network will be created.
Okay.
Do you understand? So
Yes. Understood.
and you're calling,
Sir,
yeah,
So what does 512 mean over here?
512 means so here this is 1 2 3 4 5, so instead of that 512, meaning 512 number of neurons in this layer.
So in the hidden layer.
Yes, in the hidden layer there are 512 units. So
Why
this can be
not
anything. It
like
doesn't necessarily have to be 512. You can put 1024 here. It's just a rounded number.
So also when we did model input, it gave a tensor of size 10 and it had some decimal values. You said that they are labels. What does that exactly mean?
I'm not sure I understand. So you have your input, which is an image, which is of size 28 by 28, which you reshaped to size 784, and
When you
each
type this,
yeah,
when you type this model, you got a tensor that was
you got a output of the model. So it's not a label yet. It's an output. So your model is taking some numbers. It's returning some numbers, and the output that it's returning is of size 10. And you do not know till right now what each of those numbers mean, but you're getting 10 numbers, and each of those numbers correspond to you can think of it as think of it like a score corresponding to each of the labels. So the model is saying, oh, the first number, it might be the first number with this much probability, it might be the second number with this much probability, it might be the third number with this much probability, and so on. The model is not saying, oh, it's this number. The model can never be sure. The model is saying it might be this number, it might be this number, but with this much probability. It's not exactly probability. It's from minus infinity to infinity right now, but we will come to that. The model is returning some numbers that correspond to some score that is associated with each of the numbers or each of the labels. You chose 512. It's a random. You can choose whatever you want. I chose 512 because it's a reasonable size. You can put 1024. It doesn't matter. Okay. So you pass your input through the model. You get an output which is of size 10. And what you do with this output, we'll see later. Okay. So now we have data. Now we have a model. And now what you do with this model and data is called training. So you pass your model data through your model, and the model has to learn, oh, this is how you classify images. So you take in images, and the model should learn to say, oh, this is a 1, this image contains a 3, this image contains a 5. And the process of making the model learn that is using training data is called training the model. And for training the model, certain things are required. The very first thing that's required is called a loss function. So what is a loss function? I'm not sure if Sarah has covered this. A loss function, so you're passing an image, say you're passing an image through the model and you get an output, but then is the output good or is the output bad? The model does not know that. Someone has to tell the model. There should be a signal that tells the model, okay, the output that you've created is this bad, the output that you've created is this good. There should be a quantitative measure of how good or bad your output is. For that exact reason, you use something called a loss function. So what you do is you take your image, you pass it through the model, you get some output, and then you take that output and you take the target labels. So there are some ground truth labels, there are some labels that should the correct labels, and you take those correct labels. You also take the output of the model, and then you send both of them to the loss function, and then you tell the loss function, please tell me, is the output of my model good? And the loss function will look at your output, it will look at the actual labels, and it will give you a number that corresponds to how good or how bad your model is performing for that single image. And based on this loss function, you'll train your model using different kind of optimization algorithms that Sir will cover later. That's not the focus today. So a loss function, essentially what it does is you take the output of a model, you also take the actual output, what it should have actually predicted, and you pass both of them to the loss function. And the loss function looks at both of them and it says, oh, okay, so you've passed me this, but the actual thing should be this, and because of that I'm giving you a numerical output which tells you how good or how bad your output of the model is. There are various kinds of loss functions. So if you go to TOS documentation, um, so if it's standard loss functions are implemented in TOS.NN. So if you see, there are various kinds of loss functions that are already implemented in PyTorch. There's L1 loss, there's mean square error loss, there's cross entropy loss, there's various kinds of losses. So you can look over this later. So the loss that we'll be using is something called a cross entropy loss. Right. This one. So cross entropy loss. So here you can see a cross entropy loss takes in an input and it takes in a target, and it gives you some number that tells you how good your classification is. So the whole goal of this model is you have to classify, is my image a 1, is it a 2, is it a 3, or is it one of 10 labels. So the whole goal is the model should classify as good as possible. And for classification, a standard loss that is used is something called a cross entropy loss, again which is something that Sir will cover in class. I don't think he has covered till now, but this is something that what we'll be using to train the model. So the whole goal of training is to make your loss as small as possible. So loss is something that you inherently want to make as small as possible, and the whole goal of training is you want to make a model such that you pass your input to the model, and the output you pass through the loss function, and the loss function should return as small a number as possible. So that is the whole goal of training. So let's create a loss function. So let's call it losses nn dot cross entropy loss. I think it's cross entropy loss. So this is the loss function that we'll be using. We also need an algorithm that will optimize the model. So the model initially starts with random weights, and then you want to tune the weights of the model so that finally this model is going to do classification, which is what we want to do. So in order to tune the weights of the model, there has to be some optimization algorithm that looks at the loss function and says, oh, change your weights in this manner so that your output is better. So there are many kinds of optimization algorithms. There's so the most basic one is gradient descent. There's like various kinds of optimization algorithms that are based on gradients. There's something called Adam. So here right now we'll use something called called SGD, which is stochastic gradient descent. And you do not have to know. If you already know, great. If you do not know what stochastic gradient descent is, you do not have to know right now. It's just an algorithm that takes your loss, looks at all the gradients that have been computed by PyTorch, and it changes the weights of the model. It modifies the model such that the output should be better. The output becomes better and better throughout the course of training. So right, for optimizer we have to import something called and this optim contains this optimizer called SGD, which stands for stochastic gradient descent, which is just an optimization algorithm. And this optimizer works on model.parameters. And we have to specify learning rate. Let's specify something for now. I'll explain what this is later. So just understand that there's some optimization algorithm, and we're using SGD for now. And this SGD is going to use the model parameters. So if you run model.parameters, okay. Okay. So our model. Wait. Okay, so just understand that there'll be weights corresponding to your neural network. So there will be weights corresponding to each of these connections, and our goal is to fine tune these weights based on your loss function. So who will fine tune these weights? The optimization algorithm will fine tune these weights, And the optimization algorithm that we've chosen is something called stochastic gradient descent, or SGD. And this SGD needs the parameters of the model. So it needs the weights corresponding to each of these connections, and it will be altering these weights. So we have to pass the weights of the model, and that is exactly what we've done. So to the optimizer, we have passed the weights of the model, and there's some hyperparameter called learning rate, which is not important. Um, it's just a hyperparameter that's specific to this optimizer. Did somebody raise their hand? Okay. Yes.
So when you say optimizing the weights, do you mean that we are changing the value of weight according to the gradient descent?
Yes, it's not gradient descent. Gradient descent is one algorithm, and there are many kinds of algorithms like that. So you can use any one of those algorithms to change the weights. Is that clear? Like, it doesn't necessarily have to be gradient descent. Gradient descent is the very most basic thing that you can use. There are many kinds of optimizers which are all gradient based, which all use the gradients that are implicitly calculated by PyTorch, and you can use any one of them for training. I mean, there are in certain scenarios, certain optimizers might be better, but in our case, we can just use SGD, which is a very basic optimizer. Yes, Aditya.
On this data set, can we use normal equations for optimization?
I am not sure. I think normal equations is a very it's not, it does not involve any training, right? It just takes in all of your input data, and but then, so the thing is, it's extremely computationally expensive, if I remember correctly. It's like cubic or something, right?
Yes, but it
So
will calculate the exact
yes,
minima of
uh,
the.
but then, so the thing is, you might not always have an exact minima. There might be multiple minima, multiple equally effective minima, and at the same time, how will you look at 70,000 images using your normal equations?
Yes, okay. That is why we're using SGT, right?
That is
Because
why you're
we
using a
can't.
neural network.
Okay.
Okay. Uh, okay. So, yeah, right. So we've specified a loss function. We have specified an optimizer. So now what we can do is we have to create a training loop. So what the training loop does is, it will take your input, it will pass through your model, it will pass through your model, it will get the output, and then it will take the output and it will take the targets. It will pass both of them through the loss function, and based on the loss function, it will calculate all the gradients, and based on all the gradients, it will do one step of optimization using your optimizer, whatever you specified here. Okay. So you have your training data. So one thing that we have to do is we have to normalize your data. So now your data, if you look at train at of 0, so it's a tensor, and the numbers here are from 0 to 255. So you, typically when you pass your input to a neural network, you want it to be normalized, and what you usually do is you normalize it such that it's between 0 and 1. So in this case, you can just divide it by 255, and so now everything will be between 0 and 1. You can do the same thing for validation it's as well. So right. Okay, so now your training data is ready, your optimizer is ready, your model is ready, loss function is ready. So now what we can do is we can specify certain hyperparameters. It's called hyperparameters because they are not explicitly parameters of the model that you're fine tuning, but then these also affect how good your model works. So you can have batch size. Batch size means how many images are you passing at a time through your model. So we can specify it as anything, say 100. So we have number of epochs, which means one epoch means that you have gone through all of your data one time. So say you are, so in this case, your training set contains 10,000 images. So if you pass 10,000 images through your model, you have performed one epoch of training, and one epoch of training is not enough. Like it's not sufficient that your model sees your data just one time. Typically you'll have to do you'll have to pass your data through your model multiple times. And so let's say we trained for 200 epochs, which means that you pass your data through your model 200 times. And so you have a training data which is of size 10,000, which means there are 10,000 images in your training data. So how many batches will be there in your training data? Yes.
How do we decide on the number of epochs?
It is not a fixed thing. You'll have to see. So usually when you train for more epochs, you get better results. But then past a certain point, your model will start performing worse. So there's no fixed number of epochs for which you have to train. It is a very it depends on what you're training on, what data you're training on, what model you're training. It depends upon the optimizer. It depends on a lot of things. So so I'll train it live for you, and then you can see what happens. But typically you usually have to train for more than one epoch. And because because this is very small, it's like only 10,000 images, right? So I chose a number uh, which is big enough so that we can see how the performance of the model changes with each epoch. It's not a fixed thing. It'll depend upon, you'll have to play around with this. Like maybe if you train for 300 epochs, your model performs better. Maybe if you train for 300 epochs, your model starts performing worse after say like 250 epochs. It all depends. So I'll show you how to visualize all of this. Yes, Jagmeet.
Yes, sir. This weights are updated after every epoch, or like
Weights
when?
no. So with the weights are updated after every time you pass some input through the model and you calculate the loss, the weights are updated. So after you pass batch number of images, so say you have specified the batch size here as 100. So what that means is you take a set of 100 images, you pass it through the model, and you get 100 outputs corresponding to 100 images, and you pass these 100 outputs through the loss function, and this loss function will give you a loss. And once you have this loss function, you'll calculate all the gradients using loss.backward, and then you will call your optimizer, and this optimizer will change your weights. So after you pass every batch through your model, you'll tweak your weights of the model.
Okay, sir. Thank you.
Yes, I'll.
Sir, right now you just wrote a code called for parameters and model parameters and some
Right.
It's just printing the current parameters.
Yeah, right. I just wanted to show what model.parameters exactly does. So it just points to the weights of the model, and the optimizer are going to optimize the weights of the model. So you have to pass the weights of the model to the optimizer.
So these parameters right now are just randomly.
Yes. When you create by default, it's randomly initialized. Yes. So there are various kinds of ways in which you can initialize your model so that it might perform better, which we'll discuss later. But right now, when you're just creating a model, it's usually randomly initialized by default. Yes, Aditya.
How are we deciding, like, where are we telling the model how many weights to use, or
The number of weights to use depends upon the actual structure of the network, right? So here your input is of size 784, right? So
yes?
there will be 784 of these, and then yeah,
Where are we specifying like the number of layers?
because here, when you're creating an n.linear, it automatically creates the layers. So n.linear, so here you're saying add a linear layer which takes in number of features and then which gives you number of hidden. So it'll automatically create this. So it'll create 784 units here, and it'll create 512 units here, and it'll create 10 units here.
So every time we're using the dot linear, we're creating a new layer, right?
Every time, as in yes, you're creating a new linear layer. Yes. Yes. Yes, Akshay.
Yeah, I wanted to ask what is the role of normalization here?
You can pass it without normalization through your model, but then it's typically a good practice to first normalize your data before you pass it through the model, because it usually speeds up training, and it might also give better results as well if you normalize your input before passing through the model. It's not compulsory, but then it's a standard practice. Skanda.
Can you please explain the epochs thing? Like we take the same data
Yes,
and
same
then we are
data.
passing it
Yes,
again.
it's not, so you can imagine the model as a child. So it's not necessary, it's not sufficient to just tell it one time. You'll have to tell it multiple times, because and it'll slowly learn, and it'll slowly become better and better. So it's not just sufficient to pass all the data through your model one time. You'll have to pass it multiple times.
So imagine if there are 1,000 images and our batch size is 100. This
Yes,
100
then there are
images will
10
pass
batches. There are
again.
10 batches,
Okay.
right? And then if there are 1,000 images and say you have 10 epochs, then you will pass the 1,000 images through your model 10 times. But then within one epoch itself, because your batch size is 100, you'll be passing batch by batch. So you'll be passing first batch in the first epoch, you'll be passing second batch in the first epoch, and similar till you reach 10 batches. After that, your first epoch is over, and then again you'll now it'll be a second epoch, and second epoch also you'll pass first the first batch, then the second batch, then the third batch, till 10 batches are over, and then you'll go to the third epoch and so on.
Okay, then epoch has nothing to do with the batch size.
Epoch has nothing to do with batch size. No, epoch just tells you how many times you're going over your entire data. It has nothing to do with what is internally happening.
So I can have any batch size, any epoch. That is our personal choice.
So personal choices, and there are some things that work better. And epochs, so epochs is how much you're training. Epochs is a measure of how much you're training. How many times are you passing the data through your model? Typically, more is better, but after point, it's you might get worse results. So there is some. So you train for a certain number of epochs. Okay, number of batches, it depends upon what GPU you are using. So say you have a very beefy GPU with like 64 GB of memory, then you can have bigger and bigger batch sizes, because when you're loading all of this into GPU, all of these tensors you're loading onto the GPU, right? So there has to be memory on the GPU, and you have to perform a forward pass. You have to pass all of this through the model. You have to get the output of all of this. So there has to be memory on the GPU for all of this to happen. So you have to tune your batch size accordingly. So if I'm using a small model, I mean, if I'm using a small GPU, then maybe I'll choose a batch size of 2 or 4. But if I have like a huge GPU, then I might use a batch size of maybe up to 128, 256, even 1024. It's always multiples of 2, because that's how memory is, right?
Okay, thank you.
Yes, Jagmeet.
Yes, sir. Sir, at the start of training, how we defines the how we how we how we like weights are like what value at the start of training?
Right. So at the start of training, when you instantiating this classifier, so you're saying model is equal to classifier of this specific parameters. So you've created a model, but now all the weights of the model will be random. It'll be randomly initialized. It'll be like random numbers. Is that what you're asking? And once you start training, then these random numbers will be tweaked. Your optimizer will go to these numbers. It'll tweak these numbers using some optimization algorithm that you're specifying. It'll tweak these numbers slightly and slightly with each pass. It'll slightly tweak these numbers such that finally these numbers are such that this model does classification. Yes, Sahil.
Okay, sir.
Sir, in one iteration, then we are going through all the images, but at each time we are taking batch size number of.
No, you're not passing one image at a time. You're passing a batch size image at a time through the model.
Yes, that's what I'm saying. In batch size units, they're passing all the images, and when all the images have been passed, we say one epoch has passed.
One epoch is done. One epoch is done when the entire data has been passed. It does not matter. So if there are 1,000 images and your batch size is 100, then you have to do 10 batches to finish one epoch.
Yes.
Okay, so anything else? Okay, so I was planning to do training as well, but I don't think there'll be enough time to write a whole training loop and train it and then visualize the results. So maybe we can do it in the next lab. So right now what we've done is we have created a model. We have made a model, but then we haven't trained it yet. So all the weights are random. You have a model. You have all the data ready. You have specified what will be the batch size, how many epochs you're going to train it for. You've also specified the loss function, which will tell the model, oh, is this a good output or is it not a good output? You've also specified an optimization algorithm, which will actually go and optimize these weights. It will look at the loss function, it will look at the gradients, it will go and then change these weights so that you get a more and more optimized result, just as in any kind of optimization problem. So you have an optimization algorithm as well. Now what we'll do is we'll combine all of this in a training loop. We'll create a training loop which passes your model, which passes your data through your model, and it looks at the output, it passes through the loss function, it will calculate all the gradients, and then it will perform a step of optimization. It will slightly tweak all the weights, and it will do this for how many times? It will do this for epoch number of times. It will do this for the entire data, but then epoch number of times. And then slowly and slowly, you see that your model becomes better and better at classifying the image that you're passing to the model. Right. So I think I'll stop here for today because there's also a quiz, and it'll come to questions. So there's also a quiz. So I don't know about time. Maybe next time. So next time, what I was planning was to do CNNs, convolutional neural networks. So what we'll do is we'll combine both of them because we already have a image data, which is already an image data set. So it does not matter if we do simple neural networks or CNNs on it. So next time we look at both CNNs and normal neural networks. We'll train both of them. We'll train both of them on the MNIST dataset, and we'll see the results. So writing the training loop, I think it will take like at least 45 minutes because of having to explain it. So yes.
Sir, can there be multiple input features as well? Like we only took a hidden layer, input layer, and output layer.
You can have multiple layers as well.
Features as well, apart from these three layers only.
You can have as many layers as you want. This is a very simple, very small layer, very small model. So instead of having, wait, let me just go to the model. Where did I make it? Yeah, right. So here, so let's say you can have, instead of number of hidden, let's say you have number of hidden 1, and then you can add another n dot linear, which goes from number of hidden 1 to number of hidden 2, and then you can have as many of this as you want. You can add in between. Just make sure that you also add non-linearities after each of them. Otherwise, it does not make sense because it will be equal to just having a single layer if you do not add non-linearities. Right. Yes.
And sir, is it a speciality of PyTorch that it implements the neural networks in a like of an object-oriented manner, or every library uses that way only?
I've only used TensorFlow and PyTorch, so I'm not sure about other libraries, but typically, yes, this is how we do it.
Okay.
Because how else would you do it?
When do weights of the neural network get updated, like after every epoch or
after you pass a batch of images, after every batch? So you take one batch of images, you pass through the model, you get some output for that batch, and then for that batch itself you'll compute the loss, not for one epoch. For that batch you'll compute the loss, and then you'll compute the gradients for that batch, and then you will also do a optimization step for that batch. So you'll do backpropagation and optimization at every batch. It's not at every epoch, it's at every batch, because at every epoch it's too big, right? It's seeing too many images at a time, so the change in the weights will be very wait, let me just look at the queue. I'm not sure. Yes, Aditya.
But in this case, we're using stochastic gradient descent, right?
Yes.
Not batch gradient descent.
Batch gradient descent means that the batch size is equal to number of training data. And stochastic gradient descent is a version of it where your batch size is not equal to the number of training examples. It's a smaller. So instead of your batch size being 10,000, your batch size is 1,000 or 100, which is smaller, a subset of it. That is stochastic gradient descent. If you're using batch gradient descent, it usually means you're looking. I mean, it's terminology, right? Like it depends. Sometimes people call this as batch gradient descent as well because you're taking a batch.
Okay.
Sometimes people call stochastic gradient descent as when you're doing updates on every weight. So it depends. Like usually, SGD refers to having a small mini batch, like a small batch,
Few examples at a time.
right?
Okay.
I mean, if you are confused at any point, just look at the documentation because like terminology is always like different people will use different things. So if you're ever confused, just look at. So you saw that this is optimizer is in torch.optim. So just go to documentation and look at torch.optim, and then you can see like torch.optim.sgd, and then you can see what exactly it does, what it takes, what all parameters it has. You can see what exactly it does. Everything will be mentioned there. There'll be examples as well, so you'll be clear about it.
I got confused because the algorithm, the way it is derived, we treat it like the batch size is treated as one. So
When you're
how
doing
is it?
STD, right? Right. I mean, so that is, I think, in the DL course also on Coursera, I think that is how they refer to it as SGD. But then usually, I think in PyTorch, this is what SGD means.
Okay.
Is there anybody else? I think somebody Saftar or something. Somebody had a doubt. Yes, Srishti.
So after every epoch, is the order of batch changing?
Um, it can,
What are the
it can, it can change. So it's up to you. Typically, so right now, right now, if we need not change it because it's very small data. But then usually, if you're training like huge networks, it's typically a good idea to shuffle it. It does not matter what order you pass it through, though, right? Because
no, but you said that the weight is changing after every batch.
it is
The
changing after
order
every
of the
batch,
weight. Huh.
right? So
So the order, if you're changing the order, so this will also be affected.
it
No?
will be, it will be, yes. So it's typically a good idea to shuffle it because then there's a different order of data that your model is seeing in every epoch instead of it being the same order of patches.
Is the data also shuffled?
You
Like
can,
if
in
at
this
first
case
you
we did
have
not
got
shuffle it, but then you can shuffle it. It does not matter because like essentially a model has to see the entire data, and it's, yeah, usually when you write like training loops, you usually shuffle the data before you pass it to the model. Yes. um yes.
So, sir, today, like in some, we have taught about tensors, and that we can have some operations on those tensors, and then the tensors can store the gradients or they will not store the gradients, and then we learn how to train a model.
We didn't learn how to train a model. We learn how to create a model. We learn how to basically make a model, and we also saw how to load a basic data set. And we specified loss functions, and we also specified an optimizer. We haven't done the actual training. The training, it will take time, so maybe we can do it in the next class, next lab. So there's a quiz. So this time Sarah's made the DL labs also as evaluative, and it's only a 15 minutes quiz, so it's not much. It's not that difficult. Plus, it's open book, and you should refer to the documentation if there's anything that you don't know. It's and so I recommend not using your mobile phone because I mean mobile phone you can use your mobile phone, just don't take the test, attempt the test from your mobile phone, because then if there's autocorrect, the functions will be like automatically, the case will change. So if you type toss dot something, toss dot once, and then the O is capital, then you will not get marks. So just make sure that you're, so I recommend that you take the test from your laptop or your PC, whatever you have. So the test will be of 15 minutes. You'll have to write like 1 or 2 lines of code for some of the questions, and it'll be pretty easy. Just if you don't know anything, just Google it or look at the documentation. Yeah, there are only 5 questions, and that's pretty much it, I think. Do you have any more questions? Otherwise, I'll just put the link for the lab quiz. Okay. So what am I doing? Yeah. So you can start attempting this now. It's 15 minutes, and you can submit it, and I mean, you don't have to stay in the meeting also. Like, you can leave right now after you have opened the form. I'll stop recording that.